Hello, everyone, and welcome to the webinar channel of the Association of Certified eDiscovery Specialists. My name is Mike Quateraro, and I am the president of ACED. Today, we are joined for a fantastic webinar by our partner, Ricoh. Ricoh is a leading technology and services provider in the legal and particularly eDiscovery space. And we are tuned in today for a webinar entitled The Mathematics of Technology-Assisted Review. Before we get started, please know that we love questions. We're always happy to take questions. You can submit your questions in the Q&A widget at the bottom of your screen. All questions will be anonymous. Also, if you'd like a copy of the slide deck from today's presentation, it can be downloaded from the resource widget, also at the bottom of your screen. Without further delay, I am pleased, in fact, super excited to introduce our speakers very quickly. Maura Grossman is a research professor at the University of Waterloo, a luminary in the space, and Matt Mahon, National eDiscovery Sales Manager at Ricoh. Matt, why don't you take it away?
Thank you, Mike, and thank you all for attending today. I promise to do my best, so does Maura, to make math fun. That is our goal. So we have a big agenda. I'm not going to go through every bullet point. We'll get started so we have time for questions at the end. My math teacher called me average. How mean? So if you're an average math student, that's okay. This presentation was designed for average, above average, and below average math students, and hopefully you all can learn something today. So you don't have to be a math expert to learn something and understand the concepts and definitions of the mathematics involved in technology-assisted review and validation. So a quick disclaimer, as I dreamed of putting this presentation together and my thoughts initially and ignorantly prior to more experience, I was hoping that to be very scientific, very black and white. Here is a way to validate your technology-assisted review. Here's how you do it. Here's the black and white answer to mathematical calculation. Well, there's an art to it. There isn't just one scientific way. So just please note that. There are multiple right ways. There's also bad math. So we want to make sure we avoid the bad math. So there's multiple things to consider here, including the richness of the population, your relevance of the false negatives. We'll get into that. All the statistics, don't rely on one. They say statistics lie, but we'll discuss that briefly, and proportionality.
But Matt, I would say one thing. There are some right and wrong answers here. There are some things that work and don't work. So it's not anything goes either. But there are perhaps more than one measure one can look at to determine if a project has been done well. But it's not anything goes.
That's right. You still have to follow some of the science, the mathematical calculations, and you can't just do bad math or bad statistics, because that happens. It happens in surveys all over the place. We see it throughout the world, so we don't want to apply that to our TAR workflow. So some starters with the confusion matrix to try and make it not so confusing. This actually is called the confusion matrix, but it gives you some quadrants. So you start with what your actual is. It's on the top, and then on the left-hand side, that is what your predicted. So maybe your TAR algorithm will predict. So from a true positive standpoint, those are the relevant documents that are tagged as relevant. And this is an eDiscovery review sort of terminology here. Your false negatives will be your relevant documents that the algorithm tagged as non-relevant. Your false positives are non-relevant documents that were tagged as relevant. And your true negatives are your non-relevant documents tagged as non-relevant.
Matt, I was going to say, most people don't conceptualize it this way, but it's very, very useful to create a confusion matrix, because all four of these boxes are important, not just one box.
Absolutely. You're going to see that in the calculations. You definitely need all four. And so as you can see, the yellow box there, those are your actual positive, and then the box here now shows the predicted positive. So just another way of looking at it. And we're going to use this later on for some calculations. Here's an example of the confusion matrix populated with numbers. So richness or prevalence, definition. It is the proportion or prevalence of responsive documents in a collection. The richness calculation is calculated by adding the true positives and the false negatives and dividing that by the total population size, which is why you have all 4 boxes there. So in terms of a sample calculation, in this scenario, our true positives is 23,262, plus our false negatives, which is 5,478, all divided by the total population, which gives us 28,740 divided by 100,000, and in percentage, you're going to get 28.74%.
So in other words, you're looking for all the ones you know about plus all the ones you don't know about or you missed, and then dividing that by the total population.
And then on to recall. So the definition of recall is the fraction of relevant documents that are identified as relevant by a search or review effort. And recall is going to be our true positives divided by the sum of our true positives plus our false negatives.
So in other words, recall is a measure of completeness. So you're looking at essentially the proportion of what you found over the proportion of what's out there plus what you missed.
And the sample calculation using the same confusion matrix. So our recall is going to be 23,262 divided by 23,262 plus 5,478. And you're going to get a recall percentage of 80.94%.
And another thing,
alone, that's,
oh, go ahead.
Go ahead, Maura.
Sorry. I was going to say people have to realize these aren't absolute numbers. These are estimates. So we never know unless you reviewed the entire collection before you reviewed it and you knew exactly how many responsive documents there were. We never know that. So we're trying to, with these metrics, to estimate what we think is out there. So it's important to, sometimes people speak about recall as if it's this actual thing, but we're really talking about an estimate.
That's right, and even doing a human review doc by doc, there's studies that show that humans aren't perfect either, so your recall may not be 100% accurate in that with a human review as well. So precision, the fraction of documents identified as relevant by a search or review effort that are in fact relevant. So precision is going to be your true positives divided by your true positives plus your false positives.
Right. So in other words, this is a measure of accuracy. So when you do a search, how many of the results are on point versus how much is junk. So the higher your precision, the more good stuff you're getting as compared to junk.
So a sample calculation using the same confusion matrix, 23,262, which is your true positives, divided by 23,262 plus 3,931. And so in this scenario, we get a precision of 85.54%. So I also want to briefly go through the F1 score. I know it could be a little bit more of a confusing calculation here, but it does help. We talk about not relying on one number. So just because you have a great precision or a great recall doesn't necessarily mean that your review is complete. So a definition of an F1 score is the harmonic mean of recall and precision, often used in retrieval studies as a measure of effectiveness of a search or review effort.
So basically what F1 is, it's an average, but it's a weighted average. So it's weighted towards the lesser of the recall and the precision. So whichever one is lower is going to pull that average down a little bit more.
And as you can see, you have to calculate the precision and recall prior to doing this calculation.
So, right, and F1 balances recall and precision, essentially gives equally, but oftentimes in eDiscovery, recall may be more important than precision. Finding as many relevant documents as you can may be more important than having a few non-relevant documents go through that shouldn't have. So there's actually F2, F3. There are other Fs other than just F1, but most people tend to use F1 where it counts them, again, both equally, but weights it towards the lower of the two.
So sample calculation here, your F1 is going to be 2 times 85.54% times 80.94%. That's your precision times your recall over the sum of the precision and recall, which is 85.54% plus 80.94%. So fill in that calculation out, and you'll see there's an F1 of 83.18%. Since we had a high precision and a high recall, we would anticipate that. You'll see in further calculations that with a lower precision recall, how that F1 score changes. We'll get to that later. In terms of error, the definition of error is a fraction of...
Matt, just one more thing. Sometimes where you'll see F1 used is in tools that stabilize. The TAR tools where they refer to a stabilization point, often what they're trying to do is maximize the F1. So to find that point at which both recall and both precision are maximized, you've gotten them as high as you can, and that's often behind that figure that's referred to as stabilization in a TAR tool.
Good point. So error is the fraction of documents that are incorrectly coded by a search or review effort. And so your error is going to equal your false positives plus your false negatives, which makes sense. Those are the ones that are incorrectly coded, divided by the total population size or the sample size.
And the important thing about error to keep in mind is false positives and false negatives may not be created equally. Maybe in a regular review, it would be more important not to miss something than to let some piece of junk go through. But in a privileged review, that may be very damaging. So error sort of masks which of those two are the problems. So sometimes you want to get behind that error rate that sort of smushes together false positives and false negatives because they may not be equally important to you. One may be more important than the other.
That's right. That's where some of the art of the mathematics comes in here. Is you need to understand what type of review you're doing, right? What sort of damage could be done should a privileged document be produced. So yeah, there's all different factors that you need to take into play, and then you can see which of these calculations is more important and how to optimize that accordingly. So in this scenario, we have a total of 9,409 documents. That is the sum of the false positive plus the false negative. So we have an error rate of 9.41%. So some more sample calculations. I use a different confusion matrix here just for the sake. Everyone likes to have more examples. I remember doing tutoring for math in college. There's always just one sample in the textbook. So I figured I'd give another sample here for a richness. So in this case where we have 3,421 true positives, 11,629 false positives, 30,134 false negatives, and 54,816 true negatives. In this scenario, we'd have a richness of 33.56%, a recall of 10.20%, a precision of 22.73%, an F1 score of 14.08%. So again, you see with a lower recall and precision how your F1 score goes down. And then an error rate of 41.76%, which is very high.
So I'll make 2 points here. I may have forgotten the second one, but I'll start with the first one. Be very, very, very careful about percents. Percents can be very, very misleading because 1% of 100 is a very different number than 1% of a million. So I tend to like to translate these back into the actual numbers rather than working with the percents, which can be very misleading. It's very different when you say we've missed 23,000 documents as opposed to saying we missed 1%. The 1% can look very low. The 23,000 can look very high. So keep in mind, it's often best to translate that percent back into the actual number of documents you've either found or missed, and so forth. I'll make my other point when I think of it, but it slipped my mind for the second.
No, that leads perfectly into, statistics. People say statistics lie. If the math is done correctly, it doesn't necessarily lie. It could be misleading because you don't have all the information behind how it was calculated. So, 1% seems low, but 1% of 10 million is 100,000.
You just reminded me of what I wanted to say.
Yep.
So, recall and precision are inversely related. As one goes up, the other goes down. As the other goes up, the other goes down. So you can get very high recall at the expense of very low precision if you use the search term the. The would appear in every document or just about every document, so you'd get a very, very high recall, pretty close to 100%. But it would come at the cost of pulling in tons and tons of stuff that wasn't relevant, so your precision would drop. So people act as if recall and precision are absolute, but they're really in tension with each other. And you can often get the other one higher, but it comes at a cost of the opposite one going lower.
So again, don't rely on one calculation. Really important. So in math, a lot of times you're doing proofs. You prove for 0, you prove for infinity. So I like to use extremes when trying to make a point. So in this scenario, I created a different confusion matrix where in a population of 100,000 documents, we have 33,555 true positives and 66,445 false positives. So recall. To Maura's point, if we were to produce this as 100%, we produce all the relevant documents, but at a precision of only 33.56%. So if we were to do a document dump, we'd have 100% recall, and then our F1 score is 50.26%.
And you can see that the F1 is a little is again depressed because of the extreme difference between the two.
And then, conversely, we'll go here where we'll have another confusion matrix where we have 1 true positive, 33,554 false negatives, and 66,445 true negatives. And in this scenario, we could have a precision of 100%. I found one relevant document, produced it. Our recall, though, is 0.003%, not very good. And our F1 score then is 0.006%. So as you can see, you can't rely on one number, and you definitely have a high precision that could come at the cost of recall and vice versa. So really important to not rely on one statistic, one calculation. You have to look at the full picture, and like Maura mentioned earlier, do the math and see how many documents that really is. Just be 0.003%. If you had, it may not sound like maybe a very small percentage, but again, in a large document population, if we do a lot of documents. So now we're going to get into sampling. So this is really important, as Maura mentioned earlier. Can't necessarily review every single document. We're making estimates, and so we do that through sampling. So a simple random sample is defined as a subset of statistical population in which each member of the subset has an equal probability of being chosen. So let's assume that that is our population there. And each individual would have an equal probability of being chosen. So if we're going to have a sample size of 8, we randomly choose 8 people, again, with each individual having an equal probability of being chosen, and that becomes our sample to the right. For stratified random sampling, is defined as a method of sampling that involves the division of a population into smaller subgroups known as strata, And the strata are formed based on members' shared attributes or characteristics. So we use the same 20 people, but we break out the males and the females. And now we're going to do, maybe I want a random sample of 8, but I want to have 4 males and 4 females. So now I randomly choose 4 males, 4 females, and that becomes my random sample. So
you might use that.
Use both.
Go ahead. I'm sorry.
Go for it, more.
I was going to say you might use that. So if you have in your collection very different kinds of documents or different custodians that have different amounts of documents, you might not want to do a simple random sample because something may not make it into the sample. So you might use a stratified sample to make sure that all of these different pockets of information or different custodians or different time periods make it into the random sample. So you're sort of breaking up the bigger sample into smaller subsamples and then sampling from them.
Yeah, and both are scientifically correct, but there could be, based on the art, again, a reason to use either a simple random or stratified random sample. And if you have varying documents from different data sources or custodians, stratified might be a better route. So we have 100,000 documents with 10 custodians, sort of to illustrate that here. And again, a simple random sample is an unbiased random sample from the entire population. But like Maura mentioned, in a simple random sample, you may not get documents from all 10 custodians in this scenario. You might miss a couple. And technically, the odds aren't great. Your entire random sample could be from one custodian. And from a stratified random sample, an unbiased random sample from each custodian, and in this scenario, the strata equals a custodian in the population of documents. So each document within each custodian has an equal probability of being chosen, and we're going to take a sample from each piece of the pie here. So we're going to break out one piece of pie at a time, one custodian at a time, and take a random sample from each custodian. So it's another way to illustrate and define the difference between simple and stratified. Now we're going to get into confidence levels. The definition is, as part of a statistical estimate, the chance that a confidence interval derived from a random sample will include the true value. So what does that mean? This is often misapplied. It doesn't necessarily mean that it's the odds that you're correct. It just means if you have a 95% confidence level, then that means 95% of your samples, random samples, will contain the true value within the confidence interval.
Right. Another way to put that is if you did the same experiment you did it 100 times, 95 out of the 100, you would capture within your confidence interval, which we'll talk about, or your margin of error, the actual number would be captured within that range.
And 95% you see for medical studies, that's why actually 1 in 20 studies could be technically incorrect if they're using that confidence interval and they're not applying statistics correctly or do enough tests. So this is important. And so a confidence interval, also known as the margin of error, is defined as a part of a statistical estimate, a range of values estimated to contain the true value with a particular confidence level. And I'm not going to go through, for the sake of this call, how to calculate the confidence interval. I have the calculation there, but you need a z-score chart, and we're not going to get into the madness of that mathematics in this course.
So the thing to remember is when we're doing an estimate, which all of these metrics are, it isn't going to really be exactly 85% recall. It may be between 80 and 90. In other words, there's a range around that point estimate. The point estimate is the middle number that could contain the actual number. So always remember, it's not just absolute. All of these metrics are going to have a confidence interval or a margin of error associated with them, and sometimes actually that can be quite quite large.
Yes. And that's why you need to be careful to rely on just the percentages and understand how large your sample size or your total population is. So when you do that percentage, you can see the error.
Right. Plus or minus 1% may be hundreds of thousands of documents.
Yep. If you phrase it as plus or minus 1%, it sounds great. But if I said it was plus or minus 1 million documents, it sounds very different. So point estimate, also known as a sample mean, is defined as the most likely value for a population characteristic when combined with a margin of error, or confidence interval, and a confidence level. It reflects a statistical estimate. So it is the mean of your sample, which we'll get into in a minute. So clearly. So simple random sample size calculation. Again, we'll go back to our 100,000 document population. Instead of going through all the statistics and the math, again, this is for any math student here. Railsoft has a great, on the source at the bottom, you'll see the website, a great, easy to use mathematical calculation. So you can choose your margin of error. So in this scenario, we picked 2%. You can choose your confidence level. We chose 95%. We choose our population size, which is 100,000. And then we keep the response distribution at 50% because that maximizes your population size. We're not going to get into that right now. And then your recommended sample here is 2,345 documents. So that is our sample. So to do a point estimate calculation, we're going to assume the following. Again, after reviewing the 2,345 documents that we just calculated from our sample size, there are 500 are relevant and 1,845 are tagged as not relevant. That's our point estimate is 500 divided by 2,345, which is 21.32%. So what does this mean? That's a key part of applied mathematics. What does it actually mean? So in this scenario, our point estimate represents the estimated richness of the population. Thus, we estimate that the document population contains 21,320 relevant documents, plus or minus 2%.
And again, I would put that,
2,000.
Right. Put that 2% into numbers so that you know the 21,320 relevant documents plus or minus how many relevant documents, because that's going to be more meaningful to you than plus or minus 2%. Plus or minus 2% may look very small when, in fact, it's very large.
And this pie chart represents the estimated non-relevant and the estimated relevant. So confidence interval calculation, remember we have 21,320 documents that are relevant, plus or minus 2%. And 2% of the 100,000 documents is 2,000 documents. That's our confidence interval ranges from 19,320 to 23,320 documents. So in a small population like 100,000, it's still significant. You got 4,000 range, but again, if you're dealing with millions of documents, that range could be very large when you calculate it from a document standpoint.
And in fact, I've seen it go from 0 to 2 or 3 times the number of documents in the point estimate. So then you can realize that your sampling is not particularly helpful when that happens.
Yeah, we'll get into that a little bit later as well. That's exactly right, especially in a low richness set. So in terms of benchmark, our goal is 75% recall. Again, it's not always the case for every document review, but we're just going to utilize that as a benchmark for this review.
Although we should say that we're talking about 75% recall of the TAR tool, not necessarily the human aspect of review.
Correct. And we estimated 21,320 relevant documents. So if our estimate is correct, the review team needs to identify 15,990 documents, which is 21,320 times 75, prior to validation. I don't necessarily have to do that, but again, now we at least have a benchmark to understand how many resources we need. Can we get this review done within the production time frame? And we can allocate those resources accordingly and at least have an idea of when we should start our validation.
Right, and I sometimes have trouble with this particular approach because when you factor in the margin of error, if you only go for 75% of that middle number, but the actual number is towards the top of the range, you may be very, very off. You may be stopping way too soon. And if the number's at the bottom of the range and you're trying to get 75% of it, you may never get there because there are actually fewer relevant documents. So in my view, this is a really problematic. I think you can use it as a rule of thumb, but I think it's a very problematic way to actually measure when to stop or how well you've done.
And that's why you can look at the stabilization. There's multiple things to look at here, and that's why we talk about benchmarks in different ways. That's exactly right. And here's a kind of an example of what Maura just mentioned. So we identified 15,990 relevant documents. If the actual amount of relevant documents at the top end of our confidence interval, we've actually stopped too soon and only identified 68.57%. And if you had a wider range, you may only have identified 50%. So obviously, we haven't gotten there yet if at the top of our confidence interval range. One methodology that can be utilized, again, multiple theories here, is the illusion test. And the illusion definition is the fraction of documents identified as non-relevant by a search review that are in fact relevant. Illusion is estimated by taking a random sample from the null set and determining how many documents are actually relevant. Let's see from our pie where the null set is.
So I'm going to be a bit of a naysayer with illusion because here's the problem with illusion. If I asked you the question, I said, we just did a sample of our null set, and we found 108 relevant documents, or we found 1%. Is that good, or is that not good? Well, there's no way to answer that question, because if we found 108 out of 110, if we left 108 behind out of 110, that would be very, very bad. But if we left behind 108 and we found 20,000, then maybe that's not so bad. So without knowing how many there actually are to be found, then knowing how many you left behind is not a useful piece of information. It just doesn't tell you enough.
That's why you have to do multiple statistics and understand exactly how you're applying them. Be careful how you're applying the numbers and the math. And just here's an example of that. So assume the reviewer has identified 100 relevant documents in the null set, and your illusion is going to be 100 divided by 2,335. Again, we calculated using RailSoft what a sample size would be for our null set, and thus we would estimate that there are 3,596 relevant documents left behind in the null set, but again, with an error of plus or minus 2%. So our confidence interval is going to range from 1,916 to 5,276 documents.
And you might feel very differently between 1,916 and 5,276, depending on if you only found, say, 1,000 relevant documents in the first place. That means you've missed 4 times that or something like that. So you have to be very, very careful, I think, with illusion. Again, it can, on its own, can be extremely misleading.
Correct. So now let's assume the number of relevant documents in the null set is 5,276. So we're going to assume on the high end here, and the review team identified 15,990 relevant documents. We now estimate 21,266 relevant documents. And our estimated recall is going to be 75.19%, which is 15,990 divided by 21,266. So, are we done? Maybe, but a lot of the points that Maura was mentioning, the illusion test did not factor the number of true or false positives that the review team tagged as relevant. What is the degree of relevance? So we're talking about, again, to do a worst-case scenario for a proof. Imagine if we recalled 75% of the relevant documents, but we left behind the 25% most relevant. That would be problematic. So mathematically, it might look great, but in terms of really defending that review and from an artistic perspective, that's not very good. So
right.
We want to make sure we're also finding the most relevant documents.
So it's critical to examine the novelty and the importance of the documents that were missed, not just the number, because somebody can stuff up the production with a lot of marginal stuff and leave out the hot documents, and that wouldn't be a good production. It might hit your numerical target, but that doesn't mean it's an adequate production. So it's both the quantitative and the qualitative aspect that you have to look at.
Yeah, and most algorithms, I mean, you shouldn't leave behind the most 25% relevant documents. That would be really, really crazy and an extreme example. But again, just putting extreme out there so you kind of understand the point. Still, what if it left behind half of the most relevant documents? That would still be an issue. So alternative methods to doing a validation. Taking a stratified sample of the document population. So we talked about the difference between a simple random sample and a stratified sample. So what if we had a sub-collection of the documents tagged responsive by the review team, a sub-collection of the documents tagged non-responsive by the review team, and a sub-collection of the documents not reviewed by the review team, and utilize this for validation. Because again, back to illusion, if we use those 15,990 documents that we tagged as relevant, what if 1,000 of those were actually a false positive and weren't relevant? And we've overestimated our recall. And then from here, we can calculate our recall and precision. So an alternative method where it's still real math that you're utilizing, but a little more artistic way of maybe more accurate with that math based on our scenario. You want to comment on that?
Yeah, no, I absolutely agree. You need to look at all of the different piles because there are many places where documents can be lost or left behind. It's not just the documents that the TAR tool said were non-responsive, but humans make errors. So humans may code non-relevant documents as relevant, and humans may code relevant documents as non-relevant, and that's a third, so there are at least those three areas where you need to be looking if you're doing, if you're assessing the quality. It's not just the mistakes made by the TAR tool, but it's the mistakes made by the human. And if you've used keywords beforehand, you also need to look at the things that were missed by the keywords. So it's not just testing the TAR tool, but remember there's a human component as well that you have to factor in.
Yeah, what's interesting about validation is there's a mistrust towards TAR workflows and utilizing the algorithms, and that's why validation came into play. But technically, if you're doing a human review, validation should still come into play.
Absolutely.
Humans make mistakes too.
Yep.
Perfection is not the bar here. It's really important to note that. So another potential issue is low richness populations. Really makes your math change, especially we're talking about percentages and calculating out the number of documents. Think about a population of 10 million. And we have a 1% richness, which yields an estimated 100,000 relevant documents. a 2% margin of error means there could be as many as 300,000 relevant documents or as few as 24.
Right, exactly. This is where sampling becomes very tricky, if not somewhat useless, that you really have to do your validation much more carefully when you're in this kind of situation, and you really got to move away from those percents, because 2% may sound very low, but when you're looking at a range of 24 to 300,000, that's a huge range.
Yeah, and you may never really get within your confidence interval as well. So yeah, in this type of scenario, I mean, there's a few things. You could go back and go, well, why do we have a document population with a 1% richness? Was there an over collection done here, right? Can we go back and recollect or create a different strategy? So a lot of different things to go back and look at from the start of the matter, from identification and preservation, to see if we can help with that as well. But yeah, low richness sampling becomes an issue because from the statistical math problem, you cannot get within your confidence interval. So you really need to reach out to your experts and understand what's going on and look for alternative methods to get
right. I mean, you can do it. Your sample size becomes astronomical. If you want to get an actual statistical number, your sample size is going to be astronomical. So, then you have to use multiple criteria. I think when you're quality, quantity. Sometimes you have to say, I'm going to give up on getting it between a small margin of error, but I'm going to do this because it's going to give me a rough rule of thumb about the quality. But I understand there's a significant margin of error here.
And then calculate out that percentage so you can understand it. 24 to 300,000, I think, tells a much different story than the 2% margin of error.
Yes.
So we'll do a quick summary, go do a review of the calculations, and then take some questions. So take your time with the calculations. I mean, check your work. It goes back to just math when we were kids in elementary school. I remember taking calculus classes. A lot of times we do the calculus part correct, but we'd mess up on the basic algebra or just an addition error. So make sure you have someone to check your work. Take your time, do it right. One minor miscalculation can make a big difference, as you can see, especially the larger your document population is. Validate your validation methodology. Reach out to a peer, an expert, someone else you trust. Is this a good validation methodology for this scenario? Don't necessarily rely on illusion. Maybe you need to do a stratified sampling and validate that way. Consult with an expert or trusted peers. Check your work. Cooperate with opposing counsel. Donna talks about cooperation. That's always important. The consideration of proportionality. Again, perfection isn't necessarily the bar, so what's proportional to the needs of the case? Utilizing that along with cooperation, can you come to something that is amenable to all sides? And as we mentioned, beware of those low richness populations. Anything you'd like to add to the summary, Maura?
And run like hell from percents. Change it to numbers. Always work with numbers. You can't be fooled by numbers. You can be fooled by percents. And, this requires thought. Don't just read something in a blog and then just apply it. Really make sure you know what you're doing here. There are things that work, and there are things that can be very misleading, and you want to make sure, both if you're doing the production, you want to make sure you've done a good job. And obviously, if you're receiving the production, you care dearly about that. So these are important things to understand in more than just a superficial way.
Yeah, really you want to understand the result and the outcome, not just have a number out there and go, oh, this is what the math told me. You need to understand it. And
right.
That will help you defend it.
And ask yourself, what is it? What am I trying to achieve here? What am I trying to learn or find out, rather than just applying a formula and throwing it into a calculator? Ask yourself, what is it that I want to know, and is this information that I'm getting, this statistic or this metric, is it answering the question that I want to know?
So here's a little appendix, a cheat sheet for you all. You can download the presentation, but also just this one page if you want to know how to calculate everything that we discussed today, and also utilize that RayoSoft site to help you with your confidence intervals and calculating your sample sizes as well. And with that, Mike, was there any questions?
Yeah, great. We've got a bunch of questions, Matt. So let me just dive right in here. Our first question early on was, what are generally acceptable recall and precision rates and F1 scores for responsive document reviews?
Read that one again.
I'll let you take that one.
What's the question?
What are generally acceptable recall, precision, and F1 scores for responsive document reviews?
That's a really hard question to answer because some things are really easy to find and some things are really difficult to find. I think if you often hear in the field the number 75% thrown around, but it's not clear exactly what that means. 75% or 80% end-to-end, meaning including the human errors and including search terms, that's a perfectly good result. But if you're getting just 75% from your TAR tool, then you have to consider all the errors that the humans make, which is going to bring that total score down. So I don't think there's an absolute number, but a rule of thumb that some have bandied about is about roughly 75% for the TAR tool alone. But I like to look at the end-to-end. I like to look at what percent of the documents of the total documents did I find, including all of this culling and review steps that I used in my process. And your goal is to get that numbers as high as you can, not to just say, I'm going to look for 75%, because you may be able to find 95% without, it may not be disproportional. You have to look at proportionality and figure that in. Mm-hmm. How many more documents do I have to review to find one more relevant one? And sometimes, reviewing 10 more is worth it in the confines of a particular case, and in another case, that may be disproportionate. So it's a sort of it depends answer, but it really does depend on proportionality and richness and lots of other things that go into the calculus, how much culling you've done, and so forth.
Okay, great. I think we touched on this a little bit, but our next question is how do we translate percent back into the actual number? I think, Maura, you touched on it a little bit. You want to expand a little bit?
So if it's plus or minus 2% and your collection is, let's say, 1 million, then you would do 2% of 1 million and then that would give you the number, and that's what you would add. So instead of saying plus or minus 2%, you would say 2% of 1 million. What's 2% of 1 million? What, 20,000 or 200? 20,000. So it would become plus or minus 20,000 to whatever your number was, instead of leaving it as a percent. You multiply the percent by the size of the collection.
Okay, great. Thank you. So this next question came in a little early on. When you say unbiased random sample, what do you mean? Just using random number generated to identify instances? Question mark.
Yeah, it just means that each document has an equal probability to being chosen for that random sample. So that would be unbiased. What can happen in terms of biased samples, when you're talking like polling for elections or whatever, is maybe someone's more comfortable speaking to males, so they're biased because they polled more males than females in a disproportionate way, or so there's certain things that can cause biasness, and actually in the real world there is a lot of bias that comes into the sample size. So the true mathematic definition is in an eDiscovery context, each document has equal probability, and you're not going through and hand picking documents based on what you want to think. Let a machine or your review tool randomly generate the doc IDs that need to be sampled.
Great, thanks, Matt. So I don't think I've ever done a TAR webinar, talk, presentation, or anything without getting this question. It's a great question. It always gets asked, and so it's worth repeating. What is the minimum size of the document population you would say is workable for a technology-assisted review project?
I'll start with this one. It depends whether you have TAR at your disposal and you're not paying extra for it. If you have it available to you and you're not paying an extra charge to use it, I mean, if it's more than a day's worth of review, I probably use it. So, you know, if it's a couple of thousand, if you can review them in one day, probably not worth the setup cost. But if it's 10,000, why not if you have it? If you're going out to buy it and you have to pay an extra charge to flip the switch, then you start to have to look at what is the cost of flipping the switch to turn it on versus if I were to do this manually. I think, you know, today with many tools you're not paying an extra charge, you know, to have TAR available to you, and if that's the case, I'd probably say 15,000 or so. But I think if you're using a tool that requires a lot of expertise and a lot of training, what some people call TAR 1.0, then I think probably that number has to be higher because there's more of an upfront cost in training the tool and so forth. If you're using a TAR 2.0 tool or a CAL, continuous active learning tool, and you can get right into that data right away, then you can get started with very low overhead. Do you see it differently, Matt?
No, I would agree. I mean, the other value potentially, I mean, everything you said is spot on, is if the TAR tool properly ranks documents, potentially you can get to the most relevant documents first if it's working optimally, if your algorithm's working optimally. Thus, you can make maybe some legal decisions sooner, so there's some value there to having utilizing a TAR workflow as well. But
right, and even to prioritize, even if you're going to review it all, you might as well review it in an order that makes sense. So, you know, probably if it's more than a day or two's work, it's worth it. If you can do it in a day or two, then probably not worth it.
Great points. Thanks. Next question. Is there a maximum illusion percentage rate that is used as a standard?
I think no. And again, as we were talking about before, illusion, without knowing how many relevant documents there are to be found, it is extremely difficult to interpret illusion. And many people say, well, I'll just use the number produced and compare my illusion to the number produced. But you got to remember, number produced includes non-relevant attachments. It's going to include mistakes that much of the research shows that humans make up to 30% errors in marking things responsive that aren't responsive. So if you use the number of produced documents and you compare your illusion to that, you're going to get a very warped warped view of the world. So I try to stay away from illusion altogether. Again, it can be helpful at telling you the quality of the stuff that was left behind, but unless you know how much is actually out there, it's like answering the question, I found 108 documents, or I found 2%, is that good or bad? Well, it matters if 2% is all of them or not. If you missed all of them because there only were 2% to find, and 2% in your illusion set, we haven't found any.
Yeah, and I wish I could come here and, like I said, provide a perfect formula with perfect numbers. Here you go. You get to this percentage. You're done. In the world of eDiscovery and review, that just doesn't exist.
Okay. Can you address the lack of necessity of calculating some of these stats with continuous active learning workflows versus a TAR 1.0 workflow? where a control set is available. Maura?
Okay. So some of the issues with the control set are this. You're at the beginning of a matter, you have a very different conception of relevance than you usually have later on in a matter. So when you're using a control set at the very beginning of the matter, before people have a really good sense of the data and what's actually responsive, that can lead you to overestimate or to underestimate, to overshoot or to undershoot by a significant degree. If there are errors, if it turns out that there are errors in your control set, it is possible that you will never reach 75% recall at all if things are miscoded in your control set. So the other problem with control sets is something we see, it's unique to statistics. It's like taking a pregnancy test over and over and over again. At some point, you are going to get you're going to get pregnant or not pregnant just by random chance, because remember we talked about confidence level and 95% confidence level. Well, 5% of the time you're not going to be in the correct range. So it is also easy with repeatedly using a control set that you will get something that tells you you're done when you're really not done. So again, it's a rule of thumb. It can be a helpful guideline, but I think you always need to do validation at the end to confirm what you think. Is the outcome, but you do that separate independent evaluation at the end to make sure. Matt, do you see that differently?
No, I'd argue you should use these calculations no matter what your methodology is. I mean, you discussed the errors that humans make. So the reason why this validation subject ever came up was because of the mistrust of a technology review workflow. We trust the machine, so we wanted to validate. But even if you just did a linear review without the use of an algorithm, you still use these calculations. So I don't think it matters what methodology you utilize.
Great.
I think, we started to see,
Go ahead, Maura.
I was going to say, we started to see the validation came into TAR first because people didn't trust the technology, and we sort of always gave manual review a pass. But, we should be doing validation of search terms and manual review as well. We shouldn't give them a pass and hold the TAR to a higher standard. Now that we know these things about precision and recall, we should consider them for any search and review that we do. Again, it has to be proportionate, but it's always good to do that confusion matrix, even if it isn't huge. It provides you with a lot of information about where errors are being made in your process.
Fantastic. As is usually the case on a webinar this size, we get more questions than we have time to answer, but I do want to ask one more question because I think it goes right to the heart of the presentation today. At what point in the review workflow do you complete the confusion matrix? After a human review of a sample? Question mark.
That's an interesting question. I guess you could do that as part of your quality control also. I mean, you don't have to wait to the end if you've gone 2 weeks into a review and you want to see how are my reviewers doing. You could have that kind of sample, even if it's not huge, say 1,000 documents or 2,000 documents, and have a senior reviewer re-review them blind, in other words, without knowing how the prior person coded them, and see how it falls out in the confusion matrix. And you may be able to say to your reviewers, hey, you're overmarking responsive stuff. There are a lot of false positives here, or you're missing a lot of stuff. There are a lot of false negatives here. So I think you can use it as a quality control, and certainly at the end of the process we'll tell you about the quality of the production. And again, it doesn't have to be huge. We don't have to always do this to some statistical percent. These are just tools that help us understand the quality of what we're doing and where those errors tend to be found.
Great, thanks, Maura. Matt, any closing thoughts?
Math is fun, like I mentioned at the beginning of this presentation. So hopefully you all learned something. I tried to make it simple. If you really break it out and understand the definition, that's really important. Again, understand what that number is telling you. And if you don't, it's okay, ask. That's why we're all here. ACEDS has a community, so we can ask what things mean, and definitely a platform to get some of those questions answered. But just don't plug them into a calculator and make a decision blindly off of a number that you get.
Yep, don't try this at home, like when they say on the TV, when they have the race car. Don't try this alone at home.
Maura, you get the final thought. Close us out, and then I'll end this.
Yeah, it takes some time to learn this stuff. It's worth learning, and I urge you again, try to deal with numbers rather than percents.
Great. All right. Thank you, everyone, for joining us on the ACEDS webinar channel. Thank you to Maura and Matt for a great presentation today, and thanks, of course, to our partner, Ricoh, for a great presentation. Please visit aceds.org for a complete list of our upcoming webinars. Have a great day, everyone.